All right, welcome back everyone to the deep dive. Today, we're diving into something that I think is really at the core of how we can make AI, especially large language models, much more efficient learners.
Yeah.
Always trying to squeeze more juice out of the data we have. And this paper, Reasoning to Learn from Latent Thoughts, really digs into that. So when we as humans are trying to learn something complicated, we don't just take the words at face value, right? We're trying to reverse engineer the thought process behind it.
Right.
And this research is kind of applying that to LM, saying, hey, what if we explicitly try to understand and model the hidden thoughts that go into generating text, the stuff that's not explicitly stated, but is implicit in the reasoning?
Exactly. Yeah. A lot of times, the actual reasoning steps that lead to the final output, the text or whatever, those aren't always stated.
Right.
So if we can somehow figure out how to get a language model to infer what those unstated thoughts are, so those latent thoughts, that's the term they use, that could be huge for making them learn more efficiently, especially when we don't have, infinite data to throw at them.
Right.
Kind of like if you're trying to learn to solve a puzzle, seeing the solution helps. But if you can understand how someone got to that solution, that gives you a much deeper understanding.
Oh, yeah. Watching them actually go through the process,
Exactly.
not just here's the finished product. So today we're going to unpack this whole reasoning to learn approach. We'll look at how it actually works, some of the results they got, especially for things like math reasoning, and even this really cool idea of language models bootstrapping their own performance, improving themselves.
Yeah, that was really interesting.
So, like I mentioned, this is a great deep dive for anyone who's really into machine learning, who wants to understand how these models tick. But even if you're just generally fascinated by AI, there's some really cool stuff here. So maybe let's start with this problem the paper highlights, this kind of looming data bottleneck.
Yeah.
We're building these incredibly powerful models, but we might be running out of food for them to learn from.
Right. Yeah. The paper talks about how, the computational power that we're using to train these models, that's increasing super fast.
Right.
Much faster than the amount of readily available human written text that we have.
Oh, I see. Okay.
So it's we're building these bigger and bigger brains, but the amount of knowledge, the amount of food for thought, is not necessarily keeping up.
Okay, so this reasoning to learn idea, that's positioned as a potential solution to this problem.
Yeah, that's kind of the big picture here. It's about making the most out of the data we do have by really focusing on the quality of the learning process. Specifically, getting the models to not just process the words, but to actually try and understand the deeper reasoning behind them.
Right.
So that brings us to this concept of latent thoughts, which I think is central to this whole paper.
Yeah, the hidden thoughts.
Yeah, they use this great analogy of think of all the text we see online, articles, blog posts, whatever. It's basically a compressed version of a much more detailed human thought process.
Right, yeah.
Right, when someone's writing, there's so much internal deliberation going on.
Yeah, for sure.
They're accessing background knowledge. There might be some trial and error that doesn't make it into the final piece.
Oh, yeah.
And it's these unexpressed latent thoughts that the researchers think are really crucial for efficient learning.
I see.
Because they contain so much contextual information. And those step-by-step reasoning steps that actually led to the final text. But when we just train language models on that final polished text,
right,
they're essentially missing out on all that rich information.
Yeah, so it's if you just look at the final answer in a textbook, you don't see the whole derivation.
That's a good way to put it.
Yeah, all the steps that the person took.
Exactly. It's trying to understand a complex scientific concept just by reading the abstract.
Oh, yeah.
You might get the gist, but you're missing all the logic and the evidence that underpins it.
Right. All of the nitty-gritty, the details. So how do they actually go about getting a handle on these latent thoughts?
Well, they explore a couple of different approaches. One of them is using what they call synthetic data.
Okay.
So in one key experiment, they used a really powerful language model, this one called GPT-4o Mini, to actually generate these latent thoughts, specifically for a data set of math problems.
Oh, okay.
And these synthetic thoughts were designed to kind of represent the background knowledge and the reasoning steps that a human might take when solving those problems.
I see.
So it's creating a step-by-step solution alongside the final answer.
Yeah, it's giving the model the whole textbook, not just the answer key.
Right.
So what happened when they trained other, less powerful models on this extra information, these synthetic latent thoughts?
Well, the results were pretty dramatic. So they used this synthetic data to continue pre-training a smaller model called Tiny Llama 1.1b. Okay.
And they saw a huge improvement in its ability to actually solve math problems. So the models that were only trained on the raw math problems, they got an accuracy of like 5.7% on this benchmark called math.
Okay.
But the models that were trained on the synthetic latent thoughts as well, their accuracy jumped to 25.4%.
Oh, wow. That's a big difference.
Yeah. So it seems like explicitly modeling this hidden reasoning can make a really big difference, at least in a specialized domain like math.
Yeah, that makes sense. Like, it's much clearer to see how, the model's actually getting to the answer. It's not just like magically coming up with it.
Right. And they also compared this approach to another way of using synthetic data, which is to create what's called chain of thought style paraphrases. So that's where you basically rephrase the reasoning steps, but you include them directly in the text.
Oh, I see.
And that method, they call it graph-cope, that did show some improvement over just using the raw data, getting about 19.4% accuracy.
But the models that were trained on the synthetic latent thoughts still did better. So it seems like directly modeling those underlying thought processes is even more effective than just paraphrasing the reasoning in the text itself.
Interesting. Okay, so using a powerful language model like GPT-4 Mini to generate these synthetic latent thoughts seems really promising.
Yeah.
But what about situations where you don't have access to a model that strong? Like, what if you want to do this without having a super powerful teacher model?
Well, that's where this bootstrapping latent thoughts algorithm, or BOLT, comes in.
Okay, BOLT.
This is one of the key contributions of this research.
So this is all about the model improving itself.
Exactly, yeah. It's designed to allow these models to get better at understanding and generating these latent thoughts without needing a really powerful external model to guide them.
So how does this self-improvement loop actually work? Like, what are the nuts and bolts?
So BOLT is based on the EM algorithm. That's expectation maximization, a common framework in machine learning. And it basically involves two steps that you repeat.
Okay.
So the first step is called the E step. In this step, the current language model tries to generate higher quality latent thoughts based on whatever it currently understands. They use a technique called Monte Carlo sampling here, which basically means, the model tries out a bunch of different ways of thinking about the problem.
Oh, okay.
And then it uses an internal score to decide which of those thought processes seem the most plausible.
So it's like brainstorming and then picking the best ideas.
Yeah. And over time, it actually gets better at generating good thoughts through this process.
Okay, so that's the E step. And then what about the M step?
All right, so in the M step, you take the original raw data and you augment it with those improved synthetic latent thoughts that the model just generated.
Okay.
And then you train a new version of the model on this combined data. And because this new model has now seen these richer latent thoughts, it should be better at understanding the reasoning behind the text.
Oh, okay, that makes sense. So it's like each time it goes through this loop, it gets a little bit better at generating those thoughts.
Exactly.
And then it uses those better thoughts to train a new version of itself and so on.
Exactly. So better models generate better thoughts, which in turn train even better models.
Yeah, it's like a self-fulfilling prophecy.
Right.
So does this actually work in practice? Like, did they see that self-improvement loop in action?
Yeah, they did a lot of experiments to test this. They looked at two main scenarios.
Okay.
One is what they call bootstrapping on fixed data. So in that setup, they kept the training data exactly the same across multiple iterations of this process.
Oh, okay.
So the question was, can the model still improve the quality of its thoughts and its overall performance, even if it's not seeing any new raw data?
Right. So just by going through this loop.
Exactly. And they found that it could. Like, they saw consistent improvements across several iterations, both on technical metrics that measure, how well the model is learning.
Okay.
Things like ELBO and NLL.
Right.
And also on the actual math benchmark.
So even with limited data, just going through this loop is helpful.
Yeah, at least for something like math reasoning, it seems really promising.
Okay. And then the other scenario was continual bootstrapping.
Right. So that one was designed to be a bit more like a real-world learning situation where the model is continuously seeing new data. So in each iteration, they trained the model on a different portion of a large math data set, and they kept increasing the size of that portion.
Oh.
So it's like the model's getting new information each time.
Right, like a constant stream.
Yeah. And they wanted to see if BOLT could still drive improvement in this more dynamic setting.
Okay, and what did they find there?
Well, they found that the models trained with Bolt consistently outperformed the baselines, where they kept the latent thought generation part fixed.
Okay.
So it seems like this self-improvement loop really does hold up, even when the model's constantly learning from new data.
So it's not just like a one-time boost.
No, it seems like it really helps the model continue to get better. And importantly, these gains didn't come from any extra task-specific data. It was purely from the improvement in the self-generated thoughts.
Okay. All right. So it seems like a genuine, like, bootstrapping effect.
Yeah.
Okay, cool. Now, the paper also mentions that increasing the compute used during that latent thought generation step can also play a role.
Right. They call that scaling inference compute.
So that's in the E step when the model is, like, trying out different thoughts.
Yeah, you give it more computational power there. Basically, by letting it generate and evaluate more potential thought processes, that increases the chances of it picking even better ones.
Oh, yeah.
Like more compute equals more brainstorming.
Right.
And the research suggests that, investing more in that thinking phase within each iteration of Bolt can really boost the training efficiency.
So both iterating this process and, like, giving the model more time to think during each iteration could potentially lead to even bigger improvements.
Exactly, yeah. Now, of course, research often has some unexpected results, right?
Yeah.
And the paper does mention some potential side effects they observed.
Oh, okay.
Particularly when they tested the models on a benchmark called GSM-8K.
Okay.
So they noticed that while the models trained with Bolt did better than the baselines on GSM-8K when they were using few-shot prompting.
Okay.
So that's where you give the model a few examples to guide its reasoning.
Right.
Their performance actually started to go down over multiple Bolt iterations.
Oh, interesting. That is a little counterintuitive.
Yeah, a bit surprising.
So any thoughts on why that might be happening?
Well, they think it might be because they were doing a lot of their training on this very math-heavy data set called fine math.
Oh.
So basically the models were becoming really good at math reasoning, but maybe at the expense of some of their more general language understanding abilities.
Oh, I see.
Which are important for GSM-8K.
Yeah.
Which is more about, general word problems.
Yeah, I get it.
And they did see some evidence to support this because when they looked at how the models did on a more general data set, they also saw a little dip in performance after a lot of training on that math-focused data.
Okay.
So it might be a trade-off.
Yeah. You get really good at one thing, but maybe you lose a little bit in other areas.
Yeah.
So it's important to think about those potential side effects.
Definitely. And the researchers emphasize that this is something that needs more investigation, especially as we think about applying these latent thought models to domains that aren't so focused on logic.
Okay. All right. So zooming out a bit, the paper also talks about how generally applicable this whole reasoning to learn idea might be.
Right.
And, like, some potential directions for future research.
Yeah.
What are some of the more, like, general implications they see?
Well, one really interesting point is that this idea of modeling the underlying thought process, it might not be limited to text. Like you could potentially apply it to other types of data as well.
I see.
So for example, think about video generation. You could try to model the creator's intent behind the sequence of scenes.
Oh, interesting.
Rather than just focusing on the individual frames.
Okay.
And models in areas like computer vision or robotics, they often have even bigger problems with data efficiency than language models.
Oh, for sure. Yeah.
So this approach could be really valuable there.
So it's like applying this decompressing idea to all sorts of data, not just text.
Right.
Very cool. And what about limitations of the current method? Like, what are some things they want to explore further?
Yeah, so one limitation they mentioned is that right now they model the latent thoughts in a very sequential, step-by-step way and for relatively short pieces of text. They call this a myopic structure. And they point out that this might not fully capture the more complex planning that humans do when we create longer content. Things like research papers, novels even.
Yeah, that makes sense.
Right. That's much more hierarchical.
So future research could look at more sophisticated ways of modeling those latent structures.
Exactly. Maybe something more hierarchical that reflects how humans plan and reason over longer timescales.
Like not just individual sentences, but like the whole arc of a story or an argument.
Exactly. Okay, now, another important thing is, we want these models to be able to take what they learned during pre-training and apply it to new specific tasks. So how do models trained with this latent thought approach do when it comes to those downstream tasks.
Yeah, can they actually use this new way of thinking to solve concrete problems?
Yeah, that's the key question. And the paper shows that they can.
Okay.
For instance, they showed that these models can be prompted to do chain of thought reasoning directly in the latent thought space.
Oh, interesting.
On tasks like solving math problems from the math benchmark.
So it's like they've learned to think in this more structured way.
Right.
And then they can apply that to new problems.
Exactly. And the appendix of the paper actually has some really cool examples of how these latent thoughts capture both the background knowledge needed to solve a problem
Okay.
and the step-by-step reasoning process. They have examples from algebra, combinatorics, number theory, even those word problems from GSM-8K.
Okay.
It's really interesting to see how the model seems to be actually thinking through the steps.
So it's not just pattern matching. It's actually like learning to reason.
Right. It seems that way.
Cool.
Yeah.
All right. So the paper also has a bunch of technical details about their experiments.
Yeah.
Which might be interesting to some of our listeners. Were there any particular things that stood out to you?
Yeah. So for the technically inclined, they mentioned using the TinyLama 1.1b model as the base in several of their experiments. Yeah. And they also give details of their training setup. You know, things like the optimizer they used, the learning rate schedule, batch size, all that good stuff.
Right. The nitty gritty.
Yeah, exactly. And when it came to evaluating the models, they used standard benchmarks like math, GSM-8K, MMLU STEM.
Right.
And they mainly used few-shot chain of thought prompting, both with established prompts from previous research and some synthetic prompts generated by GPT-4 Mini.
Okay.
And they also clarified that they used GPT-4 Mini as a proxy for like human level reasoning when generating the initial synthetic latent thoughts.
Okay. That makes sense.
Right. So it's like we're using this really powerful model as a stand-in for what a human might think.
Yeah. Yeah.
And for those who are really curious about the kind of knowledge these latent thoughts might be capturing, they give some really fascinating examples. Like everything from the concept of decentralization and principal component analysis to, you know, more complex physics concepts like frame dragging, showing how even seemingly simple text might have all this deep conceptual stuff underlying it.
Oh, that's cool.
And they also provide examples of latent thoughts that kind of elaborate on mathematical derivations and even show how the model can generate latent thoughts for like basic math concepts like factorials or percentage calculations.
Okay, yeah. So it seems like it's capturing a lot of different types of knowledge.
Yeah, definitely. And I think it's worth noting that they also included some examples in the appendix where the bootstrap models didn't do so well on GSM-8K.
Okay.
So it's a more nuanced picture than just like everything works perfectly.
Right, right. Good to see that honesty. All right, so to kind of wrap things up, what would you say is the most important takeaway from this research?
Well, I think the core message is that this idea of explicitly modeling the reasoning behind text generation. It seems like a really promising direction for making language models much more efficient learners.
Okay.
Especially when data is limited.
Right.
So by basically teaching these models to reason to learn, this approach has the potential to significantly improve their performance, especially in areas that require strong logical reasoning.
Okay.
And it even opens up this possibility of models that can improve their own reasoning abilities over time.
Yeah, like learning to learn.
Right.
Very cool. And what do you see as the broader implications of this kind of work for the future of AI?
Well, I think it has some really interesting implications for how we might scale these models in the future, especially if the amount of training data doesn't keep up with our computational power.
Right, right. Yeah, that data bottleneck.
Exactly.
Yeah.
And it also suggests some new ways we might be able to make these models more like robust reasoners by training them to not just process the words, but to actually understand the thought processes behind them.
Yeah, to get to that deeper level of meaning.
Right. And that could lead to, you know, more capable, more reliable AI systems in all sorts of applications.
Yeah, I mean, it feels like we're moving beyond just training models to recognize patterns and towards something that's closer to like actual understanding.
For sure.
So to our listeners, as you're thinking about this research, I'd challenge you to consider how this idea of explicitly modeling latent reasoning could be applied in other areas of AI too, not just language.
Right.
You know, could we use similar techniques in things like computer vision, robotics, even reinforcement learning?
Yeah.
It's a really fascinating area to ponder. And you can definitely learn more by checking out the paper itself and looking into some of the related work in this area.
Yeah, great suggestion.
So thanks for joining us on this deep dive.
My pleasure.
We'll see you next time.
See you then.